All right, welcome to your Chem 371 video lecture about diodes. So diodes, the most general definition is that it is a device that allows current to flow in only one direction. And in circuit diagrams, this gets the symbol, a little triangle with a line. And that means that current is flowing this way. And this is very, very useful for things like amplifying currents, rectifying currents. You will see it all over the place in circuit diagrams. So historically, they were made by using vacuum tubes, which we'll talk about a little bit more in a couple of weeks, but those are energy intensive and large devices that have largely been completely replaced by semiconductor diodes now. So we should talk about what semiconductors are. So semiconductors are crystalline materials that have intermediate conductivity between that of conductors and insulators. Generally, in this class, we're going to mostly talk about crystalline forms of silicon and germanium. You could also have semiconductor materials made out of various organic materials, or silicon carbide, germanium arsenide. So there are a number of varieties. We're going to primarily focus on the pure materials of silicon and germanium. So when we're thinking about silicon and germanium, they are both group 4 elements. They sit right below carbon on the periodic table. They both have 4 valence electrons that can be participating in bonds. And so when they're sitting in a lattice, we tend to think of a very well-ordered lattice for these. And each atom is going to wind up having 4 bonds with all of its neighbors. And there clearly aren't free electrons that aren't involved in the bonding. So that's why it's not a conductor. But these are large enough elements that thermal activation at room temperature can occasionally knock loose an electron so that the electron becomes free in the lattice. And that is called being excited into the valence band of the semiconductor. And so what that looks like then is there's a positive charge on one. So you excite an electron and maybe the electron moves off to the neighboring atom and it leaves a positive charge behind it. Then the neighboring electron from this atom could jump into the hole that's left behind from the first electron that was excited and moved. And so in that way you can have some really moderate conduction happening, which is why they're not completely insulators also. So what we tend to do with these when we want that the conduction of these materials can be increased dramatically by the inclusion of either group 5 or group 3 elements. And this process is called doping. So group 5 elements, of course, have 5 valence electrons. They have 4 bonding electrons when they're inserted into the lattice. So here we'll think about a lattice that's still mostly silicon, but maybe one of these 12 has been replaced by an arsenic. And so a group 5 element, they introduce non-bonding electrons into the lattice, and those electrons are much more easily excited by thermal energy to hop off into the valence band and become mobile in the lattice. And so when that happens, we have this group 5 element that winds up with a positive charge on it, and an electron that has been excited into the valence band and now can move freely through this material and help conduct electricity. The positive charge that's left behind is relatively non-mobile because the energetics of one of the electrons from a silicon that is involved in a covalent bond entering into that non-bonding orbital is unfavorable. So the negative charge is mobile, positive is stationary. So we call this an N-type semiconductor, or a negative type semiconductor. And I'll note that it is electrostatically neutral, but the negative charge carriers are the ones that are mobile in this material, and that's why it's called N-type. Similarly, if we have the same lattice, and we dope it with a group 3 element, then that atom has a deficiency of electrons relative to its neighbors. So it's more likely to have an electron that comes in from a neighbor, gives that a relatively stationary negative charge, and then leaves a positive charge in its wake, and that becomes a hole that is mobile throughout this, throughout the lattice. So group 3 causes mobile holes, where holes equal mobile positive charges. And the understanding there is that it's not actually the positive charge that's mobile, it's the space left behind when an electron from a neighbor jumps into a positive space, leaving a positive space wherever that electron came from. So as electrons move, the positive charges move around as if they were charge carriers. So this is called a p-type semiconductor. Both the p-type and the n-type semiconductors are much more conductive than either of the pure crystal of the semiconducting material. So we can make a diode out of two semiconductor materials by bringing into contact a p-type semiconductor material with an n-type semiconductor material. So now, if we attach the positive side to the p-type side and the negative terminal to the n-type side, the mobile carriers are going to move toward the junction. And when the holes and the mobile electrons are in proximity to each other, the electrons can move from the n-type side into the p-type side holes. Meanwhile, the electrons are replenished from the negative terminal of the power supply, and electrons are removed from the back side of the p-type side to regenerate a hole, which then migrates back towards the junction. So anytime these mobile carriers are nearby each other, current can flow pretty effectively through this material. We call this forward biased, and current can flow. Now we imagine the case where we've reversed the polarity on our power supply. So now we have the positive side over here and the negative side over here. So that's going to draw the mobile positive charges toward the negative terminal and the mobile negative charges toward the positive terminal. And it leaves a zone in the middle that has no charge carriers in it. and through which no current can travel. So this is called the depletion zone. And this is called reverse bias. So that's why you can have current flowing in only one direction through this material. Current can only flow from, as I've drawn them, left to right. They can only flow from p-type to n-type materials. And we're running into this quirk of electronics history where current is considered to be carried by positive charge carriers, so we would always draw the current as going this way, even though we as chemists understand that actually the electrons are the mobile thing and the electrons are moving the opposite direction. But it's okay, it's all self-consistent. Current is considered to be positive charge, and so current is considered to flow from the p-type side to the n-type side. Meanwhile, electrons are flowing in the opposite direction. Current flows from the positive terminal of your power supply to the negative terminal. Just a little note, in this class I don't think we need to get too worked up about that. We don't really have to work with that too much, just something for you to be aware of when you're reading circuit diagrams. So tomorrow you're going to actually get to work with a diode. You're going to work with a special kind of diode called a light-emitting diode. And that emits light because there's an energetic difference between the holes over here and the orbitals that the free electrons are sitting in on the n-type side, such that when the electron moves from one side to the other, there's a drop in energy and it releases a photon. And that photon is detected as light. So there's photons emitted when the electrons annihilate the holes on the p-type side. And that is all for today.